Another way we can determine the correct electronic configuration for various atoms is by using the periodic table of the elements. And as you can see here, and as we'll discuss right now, the periodic table gives us a lot of information about when and where to place electrons within the electron configurations of an atom according to the Aufbau principle. As we know, the periodic table is developed based on the chemical and physical properties of the elements, and it turns out the number one reason an element reacts the way it does is due to its electronic configuration. So it's not surprising that we can use the periodic table to give us a lot of information about the electronic configuration of the atoms. Okay, as we know, the S block holds 2 electrons, and when you're putting electrons in the s orbitals, you're usually putting them in this region of the periodic table. So you can see that the groups 1 and 2 stand out a bit from the rest of the periodic table, and that they are 2 rows wide, and we often call this the S block elements. Okay, as we go to the right side of the periodic table and the main group elements, we can see that the periodic table over there is 6 elements, or 6 columns wide, corresponding to the 6 electrons that can fit in the p sublevel. And in between the S and the p block, as we'll now call them, there are 10 columns which correspond to the 10 electrons that can fit in the d orbitals. And down here we have the rare earth elements that are 14 columns wide, which correspond to the 14 electrons you can put into the f orbitals. So as you're filling up electrons, we know that each element on the periodic table has 1 more electron than the element preceding it. So as you look at the periodic table, you can sort of just add electrons one by one and look at the periodic table and put them in either the s orbitals if you're in the s block, p orbitals if you're in the p block, d orbitals if you're in the d block, and f orbitals if you're in the f block. Okay, now the next question is, what energy level do you fill in the specific specific orbitals as you add 1 electron in this fashion? Well, it turns out that S and P, the energy level N will equal the period number. Okay, so we can see that hydrogen has 1 electron in the 1s orbital, and it is in period 1. Sodium, its outer electrons are in the 3s orbital. It's in period 3. Okay. Same thing with P. The outer electrons in carbon are in the 2s and 2p orbital, and carbon is in s or n equals 2, or excuse me, this period number equals 2. Okay. When we're filling electrons in the d block, we know that the first d orbitals occur in n equals 3, not n equals 4, as you might think if you're looking at, okay, scandium's in the 4th period. So for d orbitals, we have to realize that the n number is minus 1 of the period number, or n equals the period number minus 1. So scandium's electrons go in the 3d orbitals. It's in period 4, so 4 minus 1 is, of course, 3. And the f orbitals, remember that these rare earth rows are in period 6 and period 7. So the energy levels that you're going to place the electrons in the f orbitals are n equals the period number minus 2. Because we know that the first f orbital we see is f equals, or in the 4th energy levels for F1 for cerium. Okay, let's take a couple look at examples of this and see what we mean. Okay, so if we wanted to determine the electrons that go into the chlorine atom, or electronic configurations for the chlorine atom, we'd start, of course, with 1s2. It has 2 electrons in the 1s orbital. So we just go to the periodic table from left to right. We're going to put electron here and here, so that would be 1s2. Going forward, we'd have to come in a third and fourth electron in 2s2 orbitals. And then we're over here into the p block. And so we're going to put all 6 electrons in the 2p orbitals. 2p6. We keep on going, and we traverse the s block again in the third period. So this is 3s2. And then finally, we come to the p orbitals here. For n equals 3, and we know that chlorine has 5 additional electrons from the in addition to the ones we put in here. So we'd finish off chlorine's electron configuration with 3p5. So 1s2, 2s2, 2p6, 3s2, 3p5. Here's the example we use for selenium. So just like chlorine, we'd go 1s2, 2s2, 2p6, 3s2, 3p6, that would give you where argon is, and then 4s2, and then we get to the d orbitals. The first time we're going to need to put electrons in the d orbitals. Again, this would be period number -1 for the n value. And we're going to put all 10 electrons in this because we're going past the transition element. So this is 3d10. And we're going to put 4 additional electrons into selenium. So this would be 4p4. Okay, and you can do that with any element using the periodic table, and just remembering that here we have the S block, the D block, the P block, and the F block. Okay, so here is another way we can write the electron configuration, and this would be a form of reduced electron configuration. Okay, what we're going to do there is we're going to put the previous noble gas elemental symbol in brackets, because that's always going to be the same for a given element, plus any additional electrons that we need to add. Okay, so if we took a look at that selenium, okay, the previous noble gas is argon. Okay, and if we go up, we can see that no matter what, argon has this electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6. So by writing argon in parentheses, that's what we mean. And so just to shorten up the electronic configuration, we can write argon in brackets to imply 1s2, 2s2, 2p6, 3s2, 3p6. That's the electronic configuration for argon. Okay, so now that we've got that argon, we're just going to write in the additional electrons that are past argon for selenium. And that would be, of course, 4s2, 3d10, 4p4. Okay, so let's write the reduced electronic configuration for lead. Now you can see that lead has 82 electrons, so that would be quite the electronic configuration. So if we, by writing its previous electronic configuration, we can cut off quite a bit of number of electrons, specifically 54, because we're going to write xenon its previous electron configuration. Okay, so past xenon is the 6s2. Then we have to go down into the F block, and so don't forget about the F block. So we'll have 4f14. Then through the D block, 5d10. And then there are 2 electrons in the 6p orbital for lead. Okay, let's write the reduced electron configuration for something a little bit simpler. How about sulfur? Okay, we can see that neon is the previous noble gas for sulfur. And so by writing neon, again, we're writing 1s2, 2s2, 2p6, the 10 electrons corresponding to neon. And then we can write 2s2, 2p4 for sulfur.